All right, here's the last video for our area and volume review. It's the last two questions on the review sheet, and these are both polar graphs, so I'm just reminding you of the area of a region bounded by either a polar graph or by two polar graphs. So just keep these formulas in mind as we go through. All right, here's two polar curves. A couple of things to point out here. If you have r equals a number as a polar curve, you have to recognize that that is a circle with a center at the origin and whose radius is equal to whatever that constant r is equal to. So out of these two graphs here, right, the r equals 3 is going to be that smaller graph of the circle centered at the origin. So by process of elimination, the larger graph there has to be the r equals 4 minus 2 sine theta. Right? You might get this as a non-calculator question, so please just keep that in mind. You can figure out what these graphs are based on the clues in the problem. So we're going to look at part A. S is the shaded region inside the graph of that circle, r equals 3, and also inside the graph of r equals 4 minus 2 sine theta. We want to find the area of S. Well, they do give us the intersection points here. They are in the first quadrant, theta equals pi over 6, and in the second quadrant, theta equals 5 pi over 6. So because the circle is such a known geometric quantity here, we can use some geometry to at least find part of this, right? We can look at this kind of region over here. Now that portion in the fourth quadrant is really 1/4 of the circle. Since I know the radius of the circle is 3, I can find 1/4 of that fairly easy, right? Pi r squared is going to be 9 pi, so 1/4 of that is 9 pi divided by 4. But that's just the part in the fourth quadrant. Now in the first quadrant, the part that's shaded red here, right? That part is going from 0, or the x or polar axis, up to pi over 6, which is 30 degrees. So it's 1/3 of the quadrant. So that additional area there is going to be 1/3 of one whole quadrant, and one whole quadrant is 1/4 of the circle. So 1/3 of my area of the quarter of the circle results in 3 pi over 4. So when I add the quarter circle area of 9 pi over 4 plus that 1/3 of a quarter circle in 3 pi over 4, I wind up with 12 pi over 4, or 3 pi. Now that's just that section on the right, because that's all bounded by the circle, not bounded by the other graph. And by symmetry, on the left side, I get the same thing. So I'm just going to multiply that by 2. And now the only area that's left that I haven't accounted for is from pi over 6, from that intersection point, to 5 pi over 6. And at that portion in there, the boundary of your region comes from the other graph, r equals 4 minus 2 sine theta. And this one you can just write an integral using the area formula between those two angles. So I'm taking the 6 pi for the region I calculated by geometry, plus area bounded by a polar graph. So 1/2 times definite integral from my starting angle of pi over 6 to my ending angle of 5 pi over 6 of r squared d theta. I'm allowed to use a calculator. Just use x on the calculator instead of theta if you're doing this on the graphing calculator, and we wind up with 24.709. All right, now not all of the parts of these questions are area related, but we will go through them because you're going to get these sections as well, so it's important to kind of review this process as well. So part B, now this is particle motion along the polar curve, and they throw a little trickiness in here. They give you not just theta as a variable, but they tell you that theta is equal to t squared, and then they're giving you the interval from 1 to 2 using t. T equals 1 to t equals 2. So what they're doing is they're making a polar curve parametric as well, right? So your x component will be in terms of t, and your y component will be in terms of t as well. So just stick with the theta to start off with, and then we'll do a substitution for t. All right, so from polar curves when you go from polar to rectangular coordinates, or the other way around. There are these conversion equations. If you want to convert to x, x equals r times cosine theta. And I know what r is. It's that 4 minus 2 sine theta, so I could do a substitution. But again, they want this in terms of t. So once I write out what x of theta is, now I'm just going to replace all my thetas with t squareds. So x of t, right, will be, everywhere there's a theta, I replace it with something in terms of t, and I know theta is equal to t squared. So I get this business here, right? And they want to know what this is equal to at -1. So I go to my calculator and, when the particle's position is -1, the x coordinate. So I figure out where that equation is equal to a value of -1. I'm basically saying y equals the 4 minus 2 sine of x squared times cosine of x squared, and then y equals -1, and I'm finding the intersection point there. But it has to be in the interval from 1 to 2. There might be more than one intersection points there. All right, so now the second part of this that we're going to look at here, part C, it says find the position vector, well, in terms of t. Well, we just found the x part of that in terms of t, so I'll use that, but I need the y part now. So I go to the conversion formula for y equals r sine of theta. I replace r once again with the function they gave me. Same thing I just did before. Replace all my thetas with t squareds, right? And they also want to know what this is equal to at t equals 1.5. Well, first, the velocity vector would be x of t, my position vector would be x of t comma y of t. My velocity is the derivative of that, so my velocity is going to be the derivative of each one of these things, all right? We already figured those out, so v of 1.5 is x prime of 1.5, comma y prime of 1.5, and I can use the calculator for the whole thing. Just use x instead of t on the calculator and take the derivative, and you're going to wind up with those numbers. You can check those out on your own. All right, last question in the polar graph section here. Last question on the area and volume review. So you've got all 4 parts. Really the only part of this that's an area review is part A. So just keep that in mind as we go through. Again, 2 polar curves, and once again you have an r equals 3. That's the circle centered at the origin with a radius of 3. So you can figure out which one is which solely based on that. All right, so inside the graph of r equals 3, the circle, but also inside the graph of the other polar curve, r equals 3 minus sine of 2 theta. Again, I've got some geometry I can use here. In quadrant 2, that shaded portion of region R there is entirely bounded by the circle, so that's just a quarter circle, right? So if my, there's the shaded in blue region there. If my radius is 3, the area of the full circle is 9 pi, so that quarter circle in quadrant 2 is 9 pi over 4. In quadrant 1, the shaded part is just bounded by the other curve, r equals 3 minus 2 sine of 2 theta. So that's going to be my radius in my definite integral there. I'm starting on the x-axis, so that's an angle of 0. I'm going up to the y-axis, so that's pi over 2. I just apply that formula. I go to my calculator, and I get that. Fairly straightforward. All right, now part B, we step away from area for a second and take a look at what they want. They want the rate of change of x with respect to theta. Now you're allowed to use a calculator here, but when they say dx d theta, you need to have something in terms of x. So just remember the conversion equation. X equals r times cosine of theta, and I can replace r with what they said. And now I want the derivative of that at theta equals pi over 6. So I would put this 3 minus 2 sine of 2 theta times cosine of theta into my calculator using x as theta. I would take the derivative of that and evaluate it at pi over 6, and I wind up with this number. All right, and that's all I'm writing on my paper. All right, part C, distance between the two curves. Well, the distance between the two curves is the outer radius length minus the inner radius length. And when I say outer and inner, I mean furthest away from the pole or the origin and closest to the origin. There would be the inner. So when I do this here, right, on the interval from 0 to pi over 2, so we're looking in the first quadrant, they want the rate at which the distance between the two curves is changing. So I got to represent the distance between the two curves first, and then I'll take the derivative of that expression because they want the rate. Rate is a derivative. So outer radius, or furthest from the pole in quadrant 1, is the circle, so that's 3. Inner radius is the other one. When I clean that up, I wind up with this. And now I want the derivative of that at pi over 3. And again, you can, of course, this should be d prime here. There we go. You can work this out on your own on the calculator. This is not that difficult to do on a calculator active question. This is fairly straightforward. And finally, part D, particle is moving along that other curve besides the circle. And now notice what changes here. Now it's d theta dt. So once again, they're combining polar and parametric ideas together here. And that rate of change of your angle is equal to 3 for all times, all t values. Now it says find the value of dr dt at theta equals pi over 6. So I have to somehow, right, use the fact that I know d theta dt and come up with dr dt at this specific value. All right, so here's the idea. I'm looking for dr dt. So dr dt, this is by the chain rule, right? I'm using kind of dimensional analysis here too. I want to get rid of the theta in my denominator and replace that with a dt. So I multiply the fraction of dr d theta, by the denominator of that fraction, d theta over dt. That's going to cancel out the d thetas, and I'll be left with a dr dt. So when I do that, right, I get dr d theta times d theta dt, which they told me in the question was 3. Right? So I have to find dr d theta. At theta equals pi over 6. Dr d theta, that's the derivative of what they gave me, is equal to -2. So I just multiply -2 times 3, and I get my -6 answer. And that covers the area and volume review. If you have any questions, please just let me know in class or email me. All right, I will see you on the next video.